For the vanishing gradient, we did not have anything in particular to the RNN, so we moved on to a specific structure or some changes in the RNN structure. Okay. Yeah. So the intuition behind those structure was how a human generally thinks. Okay. So let's suppose if you are doing some computation, like you have 5x plus y can be equal to 3a square plus 5 c equal to a plus 5b equal to a 5b 2c. Okay. Now, if suppose you have some computation like this, where a is going here, then using that you get b, and then using of a and b you get c, and make use of these you get d. Okay. So generally, like if you are suppose a small student, small child, how it will go, that he'll first compute a, then he will compute b, and while computing b, we can throw away the information of a after we compute b. Okay, let's suppose this doesn't have this. Okay. For now, yeah. 2c. Okay. So while computing b, we can throw away the information that we have for a. While after computing c, we can throw away b and c. Okay, and just making use of c, we can write the information for d. Okay, so it's what we call them as a selective read, selective write, and selective forget. Okay, for every expression, we select some amount of information that we need to remember, that we need to write, or that we need to forget. Like for the b, only the time when we are calculating for b, we need to remember for a. After that, we can forget it. And we only need to write here the information that we have for b. We do not have to write whatever we had for a and b. Okay. So selective reading, writing, and forget. These three are the things that uh, we are going to use or trying to implement a similar kind of intuition for our RNN also. Okay. Now, it might not be that much intuitive in the starting. Okay. So its intuition that was there was come from two things. One was the ResNet connection and one was the momentum. Okay. So in the ResNet, if you remember, what we were doing is for vanishing gradient problem, we had our starting point from where we are going in our forward direction for the neural network. And after some doing linear combination, we will again add our input to that point. Okay, that was our ResNet connection. And the momentum that we had that we are taking our history of the gradients, and using that history, we are trying to push our uh, convergence rate more faster. Okay, so these two things we will be starting with, and using that we are going to build intuition on how these things can help solve our RNN vanishing gradient problem. Week 8. Okay, so now what we are going to have here, for any RNN block, what we have that we have the input that is going to it, okay, xt, and there would be some hidden state transformation that will come, and that will also go as input, and we will output our hidden state. Okay, that used to happen in the vanilla RNN case. Okay, now in this the problem was that if this chain become very long, then RNN will tend to forget what was there in the starting point of the time. Okay, the sequence which you started with. Okay, now more generally, when we are going to implement this memory based thing, what we are going to introduce is the new parameters to store that information of selective read, write, and forget. And for that purpose, we create a new vector c. Okay, that will also be feed along with our hidden state vector, and of course we are going to get that also as an output. Okay, so this is called as the context vector, which is going to help us doing the selective read, write, and forget part of RNA. Okay, So starting with the simplified version of GRU, get recursive unit. Okay. The only change that we had is in some equations. The HT equation is 1 minus ZT. This is the outer product or the element wise product. Okay. HT minus 1, then ZT product with H tilde T. Okay. Now this is the partial hidden state, and ZT is sigmoid of WZ, the concatenated form of HT minus 1 and XT plus some bias. And the partial hidden state for the next iteration is calculated as tan H of WH times HT minus 1 and XT plus BH. Okay. So what is happening here? For our new hidden state that we are going to output, okay, we are multiplying it with 1 minus ZT and ZT, okay, with partial hidden state for the new state. Okay. So because that is the output of sigmoid. Okay. So it's like 1 minus lambda times HT minus 1 plus lambda times HT tilde. Okay. It's just the representative of the current hidden state. Okay. So it's kind of like we are putting some threshold value, like this much I want to write from my previous hidden state, or this much I want to remember from my previous hidden state, and this much is I want to keep from my current hidden state. So I do not want to take the full values from my current hidden state. I will just take some partial information. That how we are going to do that, we are going to learn it through the new parameters that we are going to introduce. Okay. And from the previous also, we are just going to take some amount of value. Okay. Earlier what used to happen, this information HT minus 1 was fully used to transfer. Okay. But now in the simplified GRU structure, we are not going to fully transfer it. We are going to transfer it by some weightage. Okay. So that's what it is happening. Okay. So till here, is it okay?
In this equation, this is a linear combination of certain scalar lambda. Can we interchange those two coefficients with these two h of t minus 1 and tilde ht?
No. Basically, like what the in convention is that we take ZT is basically the vector or the amount of information we want to keep for the current hidden state.
Okay.
Okay. So that's the convention we are following. So it's similar to like what the general convention we take, that sigma is the probability for the class 1. Okay. Not like 1 minus sigma is the probability for class 0.
Okay.
Okay. So that's the convention we are keeping it. That ZT is basically the amount of or percentage of the information you want to keep for the current hidden state, and 1 minus ZT is the amount of information you want to keep for the past hidden state.
Past hidden states. Okay.
Okay.
Thank you.
Yeah, one more thing here to add. This is the vector. Okay. Now,
Yes.
for simplicity, starting with, you can treat it as a vector. That's why here we have this Hadamard product. It's basically element wise. Just if you have two vector, that's the element wise operation. Okay. Now, I hope this was already there, how this concatenated vector form works. That if you have this HT minus 1 and XT, it's written like this, then you will be having a vector HT like this and X1 like this, then you will create one new vector in which the first one would be your HT minus 1 and the second one will be your XT. Okay, so if HT is a vector in 50 elements and XT is a vector in 3 cross 1, then the new vector, the concatenated form of vector, would have 53 cross 1 size. Okay, 50 from the hidden state, then you will just stack the remaining 3 from the X. Okay, so that's the concatenated form. Yes, Karthikeyan.
Can you go to this flashcard?
This part?
Yeah. This for HT tilde, why do we take tan H?
See, these are like some experimental thing that they did, and tan H worked better. That's the only explanation we have.
Oh, that's the only explanation.
Okay. Here we have the reason for using sigmoid because we want to do it with a
probability.
probability.
We have a probability that is very clear. So we add it. And then the remaining part, 1 minus ZT and then ZT. So
Yeah,
1
1
minus ZT for the previous, ZT for the current it is
current one.
indicated. But for HT is the current, right? It is the representative of current. So,
Yes, HT is the
tan
representative.
H will go from -1 to +1, right?
Hmm.
So
It just
normally for the
works
current,
that way.
we in that case for the current it can be a negative also, positive also.
Positive also.
So is there a case? Can you give an example where it should be a positive, where it can be a negative?
For the
Maybe
HT,
a small example, a real time one. For
uh,
word example, maybe I
let,
love data science. This kind of an example.
so what you want, that HT tilde can be negative or positive?
Because tan H, right? It will give a -1 to +1.
1 to 1. Yeah.
Yeah. So
So see
positive,
what.
yes, we can understand, because for the current I add something.
Hmm.
When I go for a negative,
See, this is just that tan H will squeeze all the values that you have, that you are going to get from this linear combination in between -1 and 1. Okay. So it just, we are applying here non-linearity. So for non-linearity, we needed an activation function. Okay. And for the
okay,
tan H work pattern, okay.
it is
And even if you
okay.
like see for any RNN structure, okay, they use tan H everywhere.
Okay,
Okay.
okay. It is
Only at the
this
part
kind
of
of
only at the
the
part of
product is
out,
element wise. So some will be plus, some will be minus. Element wise multiplication. Okay.
on element wise is here only.
Yeah.
Okay. Everywhere it's just vector matrix multiplication.
So element wise, some vector, it will go as a vector.
The output of H tilde, you mean?
It will go as a vector and then.
Yes, it will go as a vector here.
Okay. It will learn something.
Yes.
Okay.
Okay. So if in this
Okay.
version, what we just trying to set the intuition is, from the previous state, we are not going to pass the full information. We are going to only pass some selected information. And of course, we are not going to set this by ourselves. We will let our model learn it by itself. That how it's going to tune its parameter in such a way that the sufficient or relevant information is passed on to the next hidden state. Okay. That's just simply done by introducing more parameters to learn that. Now, previous was the simplified version of the GRU. The official version that was there in the paper was this, okay, in which the HT part is same, okay. The HT tilde part is also kind of same, okay. ZT part, sorry, HT tilde part is not same. It introduced this RT, okay, here. And the WH previously, we did not have this, okay. We are just using of HT -1 and XT. And now it's going to make use of this RT. That's R basically for selective read. Okay, you can understand it this way. Okay, so the first intuition was the same, that we want to keep some amount of information from the previous and some amount from the current one. Okay, now here we introduce one more parameter here, that for the representative that we are going to use, okay, how much information should we write it? Okay, how much information should we write it? That is going to be decided by this RT vector, and that RT vector is learned through. If you look at the equations are very much similar. Okay, so it will be easy for you to remember this. All the equation here just follow the same pattern, that we are going to apply some activation function. Then there would be this xt, which will be multiplied with one matrix. Then there will be this ht, which will be multiplied with one matrix, and bias if you want to add. Okay, both are going to give us a probabilistic way. Okay, RT is going to give us how much information we want to keep from the previous hidden state. Okay, and that will make us improve our current representation for the next hidden state. Okay, and that is used.
What is the difference between this ZT and RT equation? Only the bias term, is it?
No.
Oh,
See,
WZ, WR.
both
Okay.
are similar, only that their parameters are different. Here we have UZ
Okay,
WC
only
and
the learning will be different in ZT, and then otherwise the XTs and HT minus one is what is being used.
yeah. So that's what I said. Even for the LSTM, which will have two more equations, okay, the format will be almost same. That you will be having some U, okay, then you will multiply it with XT, then you will be having W, you will be multiplying it with either HT or some representation of HT, and then if you want to add bias, okay, and this whole thing will be by some activation function. Now it depends upon whether it is the partial representation or whether it's going to use as the probabilistic way. If it is going to use as a probabilistic way, then you are going to just multiply it with sigmoid, else you are going to pass it with the tan h. Okay, so the format of the equation is going to just follow this: u multiplied with the our input vector plus uh, w multiplied with either the hidden state or the how much information we are keeping it from, and the bias term will get added. Okay. So this uses this one more gate. Okay. Now the final LSTM just looks a little bit more complicated. Okay, there are total 6 equation. Okay, but if you look at the equations, they follow the same format. You have the weight matrix, okay, for the hidden state. Then you have U matrix for the input vector, then the bias term. Okay, and we will be applying sigmoid on that because what these are going to represent are called as the forget state, read state, or the output state. Okay, so how much information we want to forget, how much information we want to read, or how much information we want to write. Okay, selective read, write, and forget. Okay, using the gates, we are going to first get this partial candidate state. Okay, which is again nothing but the tan h of WC HT minus 1 and UC XT. Okay, now this partial candidate state, okay, how much information you want to write from this, okay, and how much information you want to forget from the previous candidate state. Okay, so that will be your new representation or the new CT, and then that CT will be passed to the tan h. Okay, and it will be multiplied with how much information you want to write for the next hidden state. Okay, multiplying with element wise operation. Okay, so that was for the LSTM.
Fulkit,
Yes.
given the same XTs and HT minus ones, how the model learn different Ws and Us and Bs?
See, we are setting different parameters here, right? So these gates have their different purpose. Okay, the forget gate has how much information it want to forget from the past state. Okay, read gate has how much information you want to read from the current state or the current representative state. Okay, and
No,
the
your explanation is clear.
hmm,
Only thing is, what is the there should be some other information or input for the model for
it
learning
has
different weights, right? For each forget gate, input read, right? There should be some other, right? Because your HT minus one and XT is the same for
yeah,
all.
input is same, but the parameters are different. It use WF, UF, BF. It
But that
is
is getting learned, right? It is
yeah,
not
that is
what.
getting learned. Okay, and that's the
What how
good thing.
how the model will understand? It will get the same XT and the same HT minus one, right?
Hmm.
How it will
Yeah,
learn something, some different weights. That's what.
we are giving it more
Maybe is there
parameters.
some other some for this gate? Forget gate will have some other additional configuration which is different than the input read gate or the output read gate and the candidate like this.
See, the only thing is we are providing model with more parameters for it to adjust its learning based on them. Okay, so forget get had its own parameters, and the way it should work is that it should have these parameters tuned in such a way that it should do a good work on forgetting the irrelevant things. Okay, so these parameter will tuned in such a way that if you pass the past hidden state and the current input vector, then it's going to give you a forget state in such a way that the irrelevant information from the uh, candidate state, it will able to forget that. Okay, for the input state or the read state, we have again a different set of parameters. So these parameters will get tuned in different way in such a way that it will work as intended for the read gate. For the output gate, it also has a different set of parameters which are different. The input that is going to the network is the same, but the parameters that it's going to learn will be different, and they will be modified and learned in such a way in which it will favor in the case of working of output gate or the write gate. Okay, so we are providing model with more parameters and flexibility so that it can learn its representation in its own way. Okay.
You mean the dimensions of W naught will be different than Wi will be different
No,
than
no, not the
S
dimension. I
Wi?
mean the parameters. So dimension would be same, of course, because they are multiplying with the same quantity.
No, only this side, right? The right side should be the same, right? And the I'm asking about the left side because you
Okay,
have X cross Y, right? Y should be matching with HT
uh,
minus 1.
yeah, but
X will be
see,
different.
no, no, no. See, why? Uh, okay. See, this FT here, okay, it will be whatever the left dimension of W, right? So if, as you are saying, let's say it is the dimension X, okay, not A times B, okay. Now, what will be the dimension of F? A, right? Okay, and this F, if you see, it will be doing the element wise multiplication with this CT minus 1. Okay, for it to be do a correct element wise multiplication, the CT minus 1 also has to be of the same dimension A. Okay, from where we are getting this CT? Okay, this is coming from this equation, and this CT minus 1 is basically going to get it from this equation. Okay, because the CT minus 1 is dependent upon this uh, partial CT also. Okay, so this CT tilde here also should have the dimension A. Okay, for that it to be here, this WC also should have dimension A, and of course it should match with the dimension of HT minus 1, so it will also have the dimension of A cross B. Similarly, here also it's going to get multiplied with IT, so IT should also have the dimension A. So WI should also have the dimension A cross B. Again, the output of CT would be what? A, because both of them here are of dimension A. Here also they are of dimension A. Only then this addition and the multiplication makes sense. And then this CT will be getting passed to the 10H. That's not going to change its dimension. And then it's going to get element wise operation with OT. So for that it to be compatible, OT also should have dimension A. For that, WO should also have the dimension of A cross B. Okay. And once we got OT as A, the HT finally we will get the same dimension A. Okay. So everywhere the WF, WI, WO, WC, okay, will have the same dimension. But the elements in that matrix will be different. WF can have the elements 1, 2, 3, 4, while WI can have the elements 5, 6, 7, 8. Okay. Dimension will be same, elements will be different. Is it clear now?
Yeah. But how it will learn is what is not clear. Dimensions are very clear
Yeah.
because
So
for
say,
the same HT minus 1, I'm still not able to understand how it will learn something unless each
see, we
gate
are
has some
providing
other
model with
input,
more
some other
parameters.
additional, some other additional input for the forget gate to say, I am forget gate, I need to work something different than
Yeah,
the input gate. Than the
yeah, of
output
course,
gate.
it has the work that is different than the input gate, and that work is getting decided by these parameters that it has. Okay, what they have is the different parameters. So the output that it's going to get will be tuned in such a way that will be different working for the input gate. Okay, so using these different parameters, we'll be learning a good representation of the forget gate and a good representation of input or output gate. Okay, so the input is going same in both forget, read, and output gate or write gate. Okay, but the way they will be learned is because of are using different parameters. Okay, so the more the parameters that you are providing to the model, the more information or representation it is able to create to produce a good output.
Okay.
Okay. Yeah. So,
Sir, can you please explain the difference between GRU and LSTM?
yeah, GRU and LSTM, it's just that GRU does not make use of the output gate, okay, or it does not have this candidate state. Okay. So if you look at the equation together, okay, it directly make use of the HT tilde here for producing the HT, while in the LSTM, it make use of this candidate state, which is treated by the fusion of the forget gate and the input gate. For that, you are going to get the candidate state, and that candidate state is multiplied with the output gate to create the next hidden state. While for GRU, you are just going to directly feed this partially done state representation to create the next hidden state. Okay. It's just that for creating the partially hidden state, you are going to use this RT gate here. Okay.
Okay, sir, and what advantage LSTM has over GRU?
See, LSTM is because it has more parameters. Okay, it has more flexibility, so it learns more better. But of course, because more parameters, so more computation will be there. So the training time for LSTM will be high. Okay, while for GRU, it was the like kind of a refined version of LSTM. So LSTM came first, then GRU came later. Okay, so they created GRU just for kind of like an improved version, but most of the time LSTM beats GRU in terms of performance. Okay, but GRU is computationally efficient because of less parameter.
Sir, I'm not able to understand the difference between input and output gate in LSTM. Can you please explain?
Yeah, in terms of equation, you will not be able to see any much difference. Okay, all the gates use the same equation format. You have the sigmoid function. In that, the input will be, you will be having one matrix that will be multiplied with the hidden state. You will be having one matrix that will be multiplied with the input vector and bias you want to add. Okay, using that you are going to get three different representation. Okay, now there we are calling them gates. Okay, for the sake of understanding. Okay, like what is the use of this FT? It will work as kind of like a forget thing for us. That how much things we want to forget from the past information that is coming to you. Okay, IT, what we call it as a read gate. How much information I want to read from my current hidden state. Okay, and LSTM uses this candidate state. Okay, so this is my partial representation of the candidate state. Okay, for the current timestamp candidate state, and how much information I want to read from this, how much information I want to forget from the past one, how much information I want to read from the current partial representation. Using the addition of these two, we are going to get the current candidate state. That candidate state is going to multiplied by passing to the 10H and multiply with the output state. So output one is kind of like work as a write gate. How much information should I write it to create my hidden state for the next timestamp?
Sir, on difference between candidate and hidden state.
Candidate state is we are creating one more state here. Okay, that's all. There's not that much difference. So you can think of them like the ResNet connection that we had. Okay, what we do in the ResNet that we
Okay.
added one more path
Mm.
to go to it. Okay, so that's what we are doing here in the HT. So let me maybe open up an image for the LSTM. What's yeah. Okay, so in the end, what the main intuition there they had, as I said in the initial, that they are using the intuition of resonate and the momentum that we had. So stop the sharing 1 minute. This is week 8. Yeah. Is my screen visible?
Yes, sir.
Yeah. Okay. So yeah, what's happening? This that is you are able to see on the screen is like a one part of LSTM layer. Okay, that you are feeding the input from here. Okay, then you are getting some output from there. Okay, so this xt is going. Okay, it's going, and from here you are going your ht minus 1 also, passing it through the sigmoid, you are going to get ft. Okay, if this xt, if you pass it to the input one, then you are going to get this it. And then you have this candidate state also. Okay, and there's this some ct minus 1 also, that is you are getting from the previous timestamp. Okay, and that is getting fed with this ot here. Okay, by the combination of this partial representation and all. Okay, so what happening here is, what was the main problem while that we were having in the vanishing gradient is, we had only one path. Okay, like one recurrent connection that we were able to make. Okay, for the RNN. Now here we have multiple paths. Okay, for the HT we have one path through CT minus 1. Okay, and one path through this also. Okay, so we have created this extra path here. So in this way, we will be having multiple paths for the gradients to flow back, so that the vanishing gradient problem will not be able to come up there.
Oh, HT has only one path, right?
No. HT is coming from here also.
No, there is a gap, right? That is only CT. From CT minus 1, CT only comes out. HT is coming from the multiplication of tan H.
See, CT
Because
has
there is
what?
a gap.
CT has CT minus 1 and CT tilde. Okay, and CT tilde has the information of HT minus 1, that is the past radiant state. Okay, and using which we are updating the vectors. Okay, so in this way, the gradients will be flow back.
So CT is for preventing vanishing gradients.
No, in general, the gradients that gets actually prevented, like it's not that much intuitive. It's getting prevented by this forget get. Okay, that's the main part of the LSTM network. That forget get prevents it, because the way it works is that if something is not useful while predicting any output, okay, if some information was not useful, then forget get will prevent it from going forward, and in that way you are going to get the less value of the output, and while flowing back, okay, you will get the less value of the gradient. So even if the vanishing gradient problem happened, that is happening because the information was not useful for us for that output prediction. Okay, and that ft is getting fused with this ct minus 1 here, so it's getting prevented here. Okay, yeah, this diagram looks a little bit confusing, but that was the main motive for using the multiple paths here. Okay, instead of one path, you are going to get multiple paths to flow back your gradients. So the vanishing gradient problem will not happen, because you will be having a different path to update your matrix. Okay, similar to what intuition we had for the ResNet or the residual connection, that you created one more path for your gradients to flow back. Okay, here you have created multiple paths. So any doubt now? Yes, Dilip.
Yes, sir. Actually, in this diagram, there is some cross and there is some plus. Can you please explain why this is so?
Okay, that cross is for like element-wise multiplication.
Okay.
Okay, you see this ft is getting crossed with ct minus 1. Okay, that was for this representation, and the plus is simply the addition. So ft will be multiplied with this ct minus 1, and this it, okay, with multiplied with this partial hidden state or the partial candidate state here. Okay, and then it will be added with this output of that. Okay, so basically the equations here, they're written in the form of this diagram. Cross is for the element wise multiplication, plus is just for the addition. Clear?
Oh, okay.
Yeah. Any more? Okay. So
How this vanishing gradient problem getting resolved?
because we
In
will be
this
having
forget?
multiple paths. Yeah. See, because we will be having multiple paths for our gradients to flow back. Okay. So the intuition was the same as we had for the ResNet. As we will be having multiple paths for our gradients to flow back, even if for some one path the gradients vanishes, we'll be having other paths for gradients to update our matrix. Okay.
Even this current path is becoming 0, I will take the previous one. Looks like that, right?
See,
Because the previous one is
if
HT
in the
minus.
final gradient, what it's going to have is everything will get accumulated together. But yeah, you will be having gradient from all the paths, okay, to update it. But if one path gradient vanishes, you will be having the other paths to update your matrices. So it won't be the situation like in the vanilla RNN that your gradient completely vanishes and you will be having nothing to update your matrix. Okay. So let me share one more diagram. This was from the degree level deep learning course. Okay. So they were showing this path, how it's flow back here. The S1 was for your candidate vectors. Okay. So what they show is like this was one path, and okay, but you will be having a different path also. So in the vanilla RNN, we will be having just one path, like from HT minus 1, we are going to HT, then to HT plus 1, like that. But in the LSTM equation, we will be having multiple paths like this, okay, for our gradients to flow back. Okay. As multiple equation are clubbed together here. Okay. So that's why we will be having a different path for your gradients to flow back, and thus your weights are get updated. Okay. Clear?
So the slide that we were looking at,
Hmm.
so was that with respect to the vanishing gradient problem, or was that related to LSTM?
That discuss both. Like that slide was how LSTM prevents the vanishing gradient problem.
So can you please explain again?
Right? Okay. Yeah. So uh, how does the LSTM prevents this? We will be having different paths for your gradients to flow back. Okay. Previously in the vanilla RNN, you just has to have one path. Okay. And that used to also have like a recurrent connection. Okay. From HT minus 1, you go to HT, then HT plus 1, and this recurrent connection will flow up. okay, to create your output. Now in the LSTM or the GR structure, the fundamental thing that we had is you had now more paths for your gradients to flow back. Okay, instead of having just one path, okay, you will be having different paths also. Okay, so like one example that they have given, that you had just this one path, then from HT you have this one path. Okay, through the gates you have this. Okay, the way their equation gets combined, you can have multiple paths for your gradients to flow back. Okay, and again the connection, okay, or the problem if something arises, that was that what happens if along these paths also the gradients become 0. Okay, now that condition, even if it happens, okay, the reasoning that they gave in the paper was that even if the gradients become 0, that is happening because the forget get output will tend to 0. Okay, in the back propagation. Okay, so that will be fine even if it happens, because what does forget get represent? It's represent that how much information it should pass, or how much information it should forget from the past candidate state. Okay, but if the forget output tends to 0, okay, that means it is saying to us that we should not keep any information from the past one. And if due to that our gradients are becoming 0, then it's okay, because that is working fine. Okay, so that was the reasoning. First one is the main reasoning, if you are not able to understand anything, that in the LSTM we have created multiple paths for our gradients to flow back. Okay, so yeah. Any more doubts? Okay. So now let's start with the second topic that we have for the gate is bidirectional RNN. Okay. So what does this do and why we need this? Okay, what was the problem that we had? Or it's related to the limitation of our one directional RNN. Okay. So for example, if I say the one who is pretty. Okay. So if we want to like predict the next word given the we have seen this much words. Okay, this was how our one direction RNN used to work. Okay, it's going to first look at this word, then the information will be passed by taking the information from this word, and then with this and this, we are going to predict the next word. Okay, that is how one direction RNN used to work. But to predict this part, if I say what it will come, the one who reviews the movie is called the critic. Okay, for it to have come up with this review word, it should have the knowledge of movies, because if I have like in place of movie, if I have here kind of like food. Okay, so then this word that is going to come here will change. Okay, so not only this direction is important, the backward direction is also important to us. Okay, we should also know what words are coming from that direction. Okay, and that's what bidirectional RNN is going to do us for us. Okay, it's going to have one loop that is going to do in this direction. Okay, another one that is going to work in this direction. Okay, so let's say you will be having this structure in which you're going to pass here your x1, x2, 3, x4. You will be having, let's suppose, h0. From that you are going to get H1. From here you are going to get H2. Now H3. Okay. For the mark of direction, I'm going to mark them like this. Okay. Now you will be having one more for backward direction. Okay. So now you're going to start it in this direction. So you can call them, let's suppose, H3 in this direction, H2 for this direction, H1 for this direction, H0 for this direction. Okay. And now for predicting the output. Okay, what you are going to do? You need both the
We will not have a H0 for the reverse. We will have the same.
We have here.
No, not from this side. How this H3 reverse will happen unless we start, because we start with the H0, right? For the
here we are going to start with H3 for that purpose. Okay.
No, H3
just like
should
we have.
Be,
yes, sorry.
No, H3 should be coming from how this happens. I don't understand that. See. Because X1 H0 you give H1, right? This H3 reverse, how it will come? X4 it
X0,
should have something
H1,
like 4.
See, for here how the computation happens, we initialize with H0.
Yeah, H0 U plus X1 W will give H1.
Yes. Okay.
Yeah. For here, come
we are,
to this, yeah. Here, can you see?
Yeah.
How H3 here, reverse direction comes?
Here we initialize with H3. Okay.
Okay. H3 will be initialized.
Yeah.
Or it will be H4. You need to give H4 from the back one. Because here also we should have U1 H something and then W1 X4, right?
So we need H4, H3. Okay. Yeah. With that, we will be able to get H2. Okay. H3 is something we will be initializing with. Okay. Now with X4 and H3, you will get H2. With X3, H2, you will be get H1. X2, H1, you will get H0. Okay. And with that, you will be N.
Okay.
Okay. Now this H0 then can be fed. Just like here we started with H0. X1, we will get H1. H1, X2 will get H2. H2, X3 will get H3. And then H3 can be like feed into the output layer. Okay.
Okay.
Now, as we need the combination of both the direction, what we do is we concatenate both of them. Okay. So the final version is represented by the concatenation form of both of them. Okay. So we concatenate. If this was my like H in this direction, some H1, H2, H3, H4. Okay. And for the backward direction, I had this H5, H6, H7, H8. Okay. Then the concatenated form is like H1, H2, H3, H4, H5, 6, H7, and H8. Okay. This will be the concatenated form of my final hidden state. From the forward pass, I should not say forward pass, from the forward direction and from the backward direction. Okay. And now this is the hidden state that is going to use to predict the or feed into the output layer. Okay. The output layer part remains same. Okay. Clear?
Clear.
Yeah. Okay. Now, number of parameter calculation for bidirectional RNN. Okay. Again, the parameter sharing will be there. But let's see. Okay. In the simple one, what we use.
Sir, what is the motivation to move away from LSTM to bidirectional RNN?
See, LSTM is still a one-directional case, right? That all the things are happening like this. Okay. The reason for moving us from a one directional RNN to bidirectional RNN is, as in this example, if I want to predict, let's suppose what will come after the one who, what will be the next word. Okay, then that next word, even if this is my sentence for the later part, it depends upon what is this next word. Okay, so if in place of food as the first thing that I wrote here, okay, that the one who reviews movie is critic. Okay, so if movie is there, then review will come. Okay, if food is there, then the cook will come. Okay, if let's suppose the one who study books as student. Okay, so if books is there, then the study will come like that. Okay, so we should have the information from this direction also. So as we need information from both direction, sometimes, not always, so we need to handle that case also. So for that, we have this bidirectional RNN.
Okay,
For the
understood, sir.
LSTM,
Thank
we did
you.
not have this. Okay, okay, because even if our LSTM is still the one directional case. Okay, param calculation. Okay, in the case of vanilla RNN, what you used to have? You used to have this WX matrix, which used to multiply with your input vector. Okay, what was used to the dimension of this? It used to the dimension of the hidden state dimension times the input dimension that was used to the dimension of WX. Then you used to have WH that used to multiply with your HT minus 1. Okay, it used to have the dimension of hidden state times hidden state. Hidden state by means the dimension of hidden state. Okay. Then we used to have bias. If you want to add the bias, then it should also have the same dimension of hidden state. Now, what will happen for bidirectional case? Okay, the only place where the things will change, okay, is this. So you will be having this WX matrix, okay, as you will be multiplying with this T, okay. Then you will be having the WH matrix, so you will be multiplying with HT minus 1, okay, and then same B will be there. Okay, now this will be just multiplied with 2. Okay, because you will be having one for the forward direction and one for the backward direction. So just that whatever the number of parameter that you simply calculate in assuming that you have just one directional case, you can just multiply it by 2 to get the number of parameter for bidirectional RNN. Okay, so parameter calculation will be simple if you know how to calculate the parameter for one direction RNN. You just have to multiply it by 2 because you need to account for the second direction. That's all. Okay, is it clear?
Is there a plus between
Yeah, plus is also there in the equation. Okay. So because you will be having one for the forward and one for the backward, so just parameter will be double. That's all.
Sir, can you please take one example here?
Yeah, sure. So you want the example for number of parameter calculation.
Yes, sir.
So let's suppose I have this x1, we have this x2, we have this x3. Okay. So if my x is in, let's suppose, dimension R5, okay, and I keep my hidden state dimension as R10, okay, then my WX matrix that will be multiplied with my NEXT, okay, will be of size what?
10 cross 5.
10 cross 5. Okay, my WH matrix that will be multiplied with any hidden state, it will be of dimension
10 cross 10.
10 cross 10. 1 minute. what you are saying. That is x or n. Okay, that's x. Sorry. It's everywhere it's x. Okay, nowhere it is n. Yeah. Okay. So let's suppose for now we ignore the bias. So if you want to add the bias, then what will be the dimension for bias?
10 plus 1.
10 plus 1. Okay. As our equation is ht is equal to some activation function wx xt plus wh ht minus 1 plus b. This is of dimension 10 cross 5. This is of dimension 10 cross 10. This is of dimension 10. Okay, so everything matches. Good. Okay. Now, for the simple one direction RNN, the number of parameter here would be 10 into 5 plus 10 into 10 plus 10. So 50 plus 100 plus 10. Okay, 160. For the bidirectional RNN, it will become just 320. Okay, as you will be having the same equation, it's just that parameter will be different. So, but the dimension will be technically same because you will be having the same WX matrix. You keep the hidden state dimension also generally the same. Okay, and the bias. The same thing will happen for the backward direction also. So the same parameter will be there. So you can just multiply with 320. Okay. Now, if you also encounter for the output state. Okay. So let's suppose this was the forward direction. Then you had something for the backward direction also. Now, if you have the output state also, okay, what goes into the output state? The concatenated form of hidden state. Okay, so if my forward hidden state dimension is 10, backward hidden state dimension is also 10, my final hidden state dimension will become R20. Okay, now this H, the concatenated vector, will be multiplied with WY. Okay, H plus some bias if you want to add. So what will be its dimension? Its dimension would be, it has to be the 20 columns for it to get multiplied with this H. And the number of rows depends upon the number of classes you have. Okay, so let's suppose if I have 5 classes, then 5 cross 20. And bias will be also then 5. So 100 plus 5 more. 150 for the output layer. Okay. Clear? Yeah. Any doubts so far? Okay. Moving on to the next one, encoder decoder architecture. Okay. So encoder decoder was first used for the translation purpose, and from where the intuition will be more clear. Okay. However, as the term suggests or as the name suggests, we have something which we are going to encode, and that will be the work for our encoder. And then we will be having something, okay, that we want to decode, and that will be work for our decoder. Okay. So if I take the example of our translation work, okay, you will be seeing that there's no guarantee that the number of, okay, so let's take the number of words as a length of the sequence. Okay, so if my sentence is, let's suppose, he went home. Okay, so this is in the English. It has only 3 words. Okay, now if I translate this sentence into some other language, then there's no guarantee that that language will also have the same number of words. Okay, so okay, for this example, I think it will be the same. Like I only know Hindi except English, so and okay. So for this, I don't know how many of you know Hindi, but if we translate this to Hindi, then like वह घर गया and उसके बाद school गया. So it can have like more words than the original language or the source language. Okay, so there's no guarantee that any translation task if you are doing, then for the source language, the language in which we have our text, and the target language, the language for which we want to translate for, okay, that both of them should have the same number of words. Okay, because till now what we were having that for our simple RNN structure, that we will be having this connection like this. Okay, so it's take like if we have 4 words, okay, then it will output 4 words only. Okay, and that was one of the problem. So this problem was solved using encoder decoder architecture. Okay, what it technically do is nothing. It will going to create 2 RNN block. Okay, one RNN will be used as an encoder to encode or to collect the information from my source language. Then that collection information will be fed into what is called as the decoder model. That is nothing but just another RNN. Okay, and because both of them are different, we can use the different number of you know sequence length for them.
Sir, is this encoder decoder being introduced as part of bidirectional RNN?
No, but here you can apply if you want. Okay, so encoder decoder is just that you are using 2 different RNN models. Okay, and then output of one is fed into the other. Okay, so here if you
Sir,
want, you
is
can.
it similar to gains that we studied earlier, generator and discriminator?
Not technically, but it is comes under like the generative part. But there also we had the 2 models, but in that what was happening, the 2 models were working in a competition kind of thing. Okay, one success was dependent upon other's failure. Here it is not. Okay, both are working towards the same goal here. Okay, so both are not fighting to each other here. So a classic encoder decoder model will be we will be having the encoder that's just one RNN. Now in that we generally do not have any output layer. We will be just having the hidden layers only or the hidden states. Okay, so the final hidden representation that you are going to get, let's suppose HT. Okay, this HT will now be fed into the decoder part. Okay, in the encoder we will be starting with some H0, but for the decoder we generally do not do that. We take the representation from the HT. This HT now contains this entire information of my source language. Okay, so this entire information is now going to feed to the decoder, which is nothing but another RNN. Okay, and then using that information, it's going to give the output. Okay, so this is what the encoder decoder architecture do. Okay, now first of all, this till this much, is it clear?
Sir, first it starts with encoder,
Hmm.
and then encoder's output feeds to decoder.
Yes, correct.
Okay.
But now there are 2-3 problems that can create if you're just directly going to use this. What are these problems? One was the error accumulation can happen. What does it mean by error accumulation? What is the input that is going into the decoder? It's basically the target language words. Okay. And what it is going to output? It's going to output the predicted word. Now, what we generally do for the inference time, we use this predicted word, and that is going to feed as a next input. Okay, but if you do this case, then what will happen is the error will get accumulated, because if any one word get predicted wrongly in between, okay, and because that word is predicted wrongly, then for due to that you will get again a wrong word prediction, and that is again going to feed it to the input to the next layer or the next sequence. So this error will get accumulated. To prevent this error accumulation, what we use is the teacher forcing. And teacher forcing is that at the training time, okay, the inputs that is going to the decoder will be the true word or the ground word. Okay, so even if the model predicts, let's suppose my decoder is like I like DL. Okay, so this is my target language. Suppose English my target language. Okay, and these are my correct words. Okay, so I'm going to feed I. Now it can predict like or DL or I. Okay, suppose I only have these 3 words for my output prediction. And when I feed I, it's going to give me a probability of what should be the next word, whether it should be I, whether it should be like, whether it should be DL. Okay, now suppose it's give DL as the most probable words. Okay, but I'm not going to use DL here for my next input. I'm going to use the true word that was there, like. Okay, and then like will be fed. I'm going to get some output. Okay, now no matter what the predicted output was, I'm going to use the true label for next word. Okay, so this is the teacher forcing. Okay, but this is only done at the training time. Okay, at the test time or the inference time, you use the predicted word only. So whatever the predicted word you are going to get, you are going to feed that word only as an input to the next one. Okay, so is teacher forcing clear?
So in this encoder and decoder, we, other than input, we also have the hidden layers and everything, right? Like other neural network, or is it just input and then?
See, it's just the encoder is just that you will be having a RNN only, but you will not be having an output layer. Okay, other things work same as what a general RNN will do. Okay, and it's just that the output of this will be HT, that will be fed as an input. Okay, for my decoder. Now there are some variants in which what we do here, what I've written is you are just going to feed it to the first time, but you might do one thing, that you are going to feed it at every timestamp. Okay, that is also something that can be done. Okay,
Sir, inside the encoder, it is RNN.
yes. Okay. Now
Sir,
it
it is
just need
single
not,
direction or multi-direction.
it depends upon which one you want to use. Okay, just use case, it just, this is the model architecture, the encoder decoder architecture. This is one that you will be having one model here. Okay, that's going to give you some representation. That representation is going to feed for your decoder. So it's like you have something that will be getting encoded by the encoder model, then you will be having your decoder model that's going to decode it for you, what it's want to say. Okay, so it works something like this.
Okay, sir.
Now, this need not to be limited to RNN. It can work with different scenarios also, like you can combine multiple models. So for suppose you want to do the work of image captioning. Okay, so you have an image and you want to give the caption to this. Yes, it's up to you what you want to use here. Okay, now generally we what I have seen is generally we go with the single direction RNN only, but I don't think so there should be any problem while using bidirectional both in both the case. Okay, yes, you can use, but it will become very computationally expensive. Okay, yeah. What I wanted to say, there I was saying that it need not to be limited to the RNN part. Okay, so for suppose if you have a work of image captioning, that is you have an image and you want to give the caption for this. Okay, so what should be the input in this case? What will be my input for this type of problem?
Image.
And what will be the output for this problem?
Text.
Text. Okay, so for image, what model you are going to use?
CNN.
CNN. For the output, what model you are going to use?
RNN.
RNN. Okay, so in that the encoder will be your CNN. Okay, for the encoder case, so you will be having this image. Okay, that will be passed with some convolution layer. That's going, you can have multiple convolution layer, pooling layer like this, and then you are going to get the flattening. Okay, after flattening, you might do one more like linear combination. Okay, now just the layer that you use for predicting the output. Okay, just before that. Okay, that representation you can take. Okay, and then that representation is going to feed to your decoder model. Okay, so maybe might have some pictures. Encoder, decoder. Okay, so this was your picture. You want to caption it. Okay, so you will be getting a representation of that. Okay, after passing it through the hidden state, you get representation, and that representation is going to then feed into the RNN as your decoder model. Okay, there might be another term problems that might have. And as I said, there were two options. Okay, one is that you pass it to the CNN, you get the representation, and you only feed it once. Another is, okay, you feed it at every stage. Okay.
Normal CNN with the head can be called as encoder and decoder because head does the decoding part.
See, what we do in the normal CNN case, you are just going to output the probability for the class if you're doing a classification problem, right? The head part. That's not going to generate a sentence for you, right?
Okay.
Okay. So what you will be getting is
Okay.
I want.
So in this case, for the training, I will send the picture to the CNN, and to the RNN, I will say I have to send a boy throwing a frisbee.
Yeah.
Like this.
So you will be having your image. You pass it to some layer. After flattening, pass it to another layer. And let's suppose this is the classification head. That this is the point where you apply the softmax function to predict the probability. Just before that, whatever you had, that is your representation vector. Okay, and that vector you are going to use. Okay, and let's suppose this is the vector, and that will be fed into the RNN now. There are two options. Either you can,
because to the head basically label will be given here. Instead of the label, we are
it is
giving
fed
this,
into RNN.
ball throwing the frisbee to the RNN.
Yeah. Yes. Okay.
It's like a variant of actual CNN only. CNN
Yeah.
with a head. CNN does mainly capturing the image, what it is.
Yeah. So
And then
CNN, what
pass
it's
it on
doing,
to the head. The head is the one which is going to actually takes the weight to classify whether it's a dog or a cat. That label is already with the head.
yeah. But here, as we do not want the labeling, what we want
Yeah,
is
here
CNN
instead
is
of
going to
label,
give
we
us,
are passing the boy throwing the frisbee or the man is walking, whatever it is. Like this, a text format we are passing.
yeah. Okay. So this was another task. Okay. So what I in the end want to say that encoder and decoder does not need to be just stop at RNN or CNN. Okay. The main funda behind encoder and decoder is if you have a task in which you want to do, like your input is something and you want to predict output which is something different, then you are going to have two models. One model is going to take your input and give you a representation of the input. So as we have this unstructured data set like image, text, audio, video. Okay. So and then you have some output which is in some other unstructured data set. Then you can have the one encoder model that's going to give you the representation for your input, and then you will pass it to the decoder to get you the final output. Okay. Okay. So that was it. Next problem. Okay, the first problem, I hope it was clear, the error accumulation, and the solution for that was we use teacher forcing. Okay, but teacher forcing is only done at training time. At the inference time, we do not do that. Okay, the next thing is the error. Okay, how do you calculate the error here? Or how do you calculate that whether the sequence that you have generated is a good enough sequence, okay, or not? So let me use the example. So let's suppose the use what was there in question one. That here. Yeah. So this is the output that we are talking about. So suppose the correct output was she landed in North Korea by accident. Okay. This is the correct output. This should be the correct output. Okay. But your model predicted that she crashed into North Korea. Okay. Now for a human, like it's good enough if you see. Okay. But how do we actually calculate this error here? Okay. Or how do we score this predicted sequence? So this was my predicted sequence. This was my original or the ground truth. Okay. So for that, we use a matrix called Bleu score. Okay. BLEU score. Okay. And what it uses, I write the formula. The exponential of min of 0, 1 minus the length of the label divided by the length of the predicted word. Okay. This part is called as the brevity penalty. Now this part will be multiplied with n-gram precision. So that is your pi n equal to 1 till k Pn power 1 by k. Okay. So this second part is called as the n-gram precision. Okay. And the first part is called as the brevity penalty. And you multiply both of them. That will be your final Bleu score. Okay. So I'll be using this example to showcase how it's done. Okay. So let's start with this.
What is blue?
Blue is the scoring matrix. Okay.
It's an acronym or it's just called blue?
It's acronym.
Okay.
Okay. So it's bilingual evaluated under study. Evaluation under study. Okay. It's the acronym for.
Sir, what is this pi k?
Pi k, this is the multiplication that is happening. I will do, we will be solving basically how we are going to calculate the brevity penalty and the score for this. Okay. So suppose this is my target sequence. This is my predicted sequence. Okay. For this, I want to calculate the Bleu score. For with that, you will be able to understand how this things works. Okay. So first, we are going to calculate this part. Okay. This is called as the n-gram precision. Okay.
Sir, n-gram is the window size?
Yeah, it's like you are going to go with unigram, bigram, trigram like that. Okay. Now, of course, you can stop at any place you want. Okay. So first, I will be starting with unigram case. Okay. Unigram case, what you are going to start off with? Okay. You will be taking each of these words. Okay. And just match, because it is say unigram, so we will be just taking every word individually. So you have 1, 2, 3, 4, 5, each of these 5 words. So he crashed into North Korea. Okay. So total length is 5. Okay. You have to match here how many of these unigram that you make are matching with the actual target one. So one is matching she, we have North, and we have Korea. So 3 are matching, right? So 3 by 5.6. That is your P1. So that type P that I wrote here, P underscore N. Okay. So P1, that is your 0.6.
Sir, is this for unigram?
Yeah, this is for unigram. So this is the unigram precision that we have. Okay. So I hope it's clear. Now let's move on to bigram. Okay. So bigram, what you're going to get, you are going to make pair of 2, but in the sequence. That is, she crashed will be one pair. Then you're going to slide the window. So crashed into, then into North, then North Korea. And after that, we do not have any 2 more words. So that's all. So our first pair would be she. Let me use another color. She crashed, then crashed into, okay, then what is there? Into North and North Korea. Into North and then North Korea. Okay, so these 4 pairs we have for our bigram. Okay, again, what you're going to do, you're going to match it with the target one. So do we have she crashed here? It should come together. She crashed. No, right? Okay. So do we have crashed into here? No. Do we have into North here? Do we have?
No.
No, right? Now, do we have North Korea here?
Yes.
Yes, right? So we have this North Korea here. Okay, so only one is matching. The totals are how many? 4 were there, and only out of them, only one is matching. So P2 is 1 by 4. Okay. Now, similarly, you can go with trigram and continue until the sequence ends. Okay, and until you get this full word. So there are 1, 2, 3, 4, 5. So for this sequence, you can only go till 5 gram precision. Okay, but for the simplicity, let's stop here, unigram and bigram, but same calculation you can follow up. Okay, and I don't think so anymore. We will be having it. Okay.
If we go 5 gram, then it will be 0, no?
Yeah, then it will be 0.
Then multiplication of probabilities will be 0.
Yeah, then it will be 0.
Okay.
But then we'll be having this power also. So 0 power 1 by something. So whatever power it is there.
Sir, what we just calculated is unigram, I mean n-gram precision.
Yeah.
Then how do we compute brevity penalty?
Yeah, we will come to that part. Yes, even for the trigram also it will be
This
0.
one, how it will become 0? Because K is gram, right?
Yeah, K is gram.
So pi means, oh, it is pi.
No, pi is the multiplication.
Multiplication only. Okay.
Yeah. So P1, P2, P3 like that.
Okay.
Okay.
Who will specify this K? To what extent we need to go?
You have to
Is
specify
it a
that.
hyperparameter?
Yes. So you have to choose it carefully. Generally, we do not go with multiple one because
You will
then
not make this term 0 at all in that case.
yeah, we do not want to make that. Okay. So generally we stop at unigram bigram. Okay. Yeah. This is basically what PA question 8, I think. Yeah, right. Yeah, question 7. So PA 8, question 7. Okay. Now, so unigram and bigram are done. Okay. Now what this term says, it's just multiplication of these two and powered by 1 by 2. Okay. So 0.6 into 0.4. Is it 0.4?
0.25.
Oh, 0.25. 0.25 power 1 by 2. Because we go till 2 here. We go till bigram precision. That's why it will be 1 by 2. If we went to like trigram or something more, then 1 by 3, 1 by 4, 1 by 5 like that. Okay. So we'll get some output. Okay. That was for just n-gram precision. But you also have the second term, that is brevity penalty. Now, what was the need for using brevity penalty is, okay, for the short sequence. Okay. So for the short sequence, okay, if you do not take into the account of brevity penalty and you just take into the account of this term only, then suppose your model, instead of this she crashed into North Korea, your model might have predicted only North Korea. Then tell me what will be the value of this term.
1.
Not 1, it's 2 by 2, 1 into 1. Yeah, 1 power anything, 1, correct. Okay. So this value will have give us 1, which is a very good score. Okay. I think Leo has any. Okay. Leo does not have any limit that is given, but this will be a very good score if you get 1. Okay. But because it is a short sequence, that is the reason we are able to get it 1. So to penalize the short sequence, we introduce this brevity penalty. Okay.
Sir, how it will be 1?
See, calculate the unigram precision. What will be its value? Both are matching, right? North is also here, Korea is also here. So
Yes.
predicted was for 2, out of them 2 of them are matching. Calculate its bigram precision. North Korea, only one pair is there. We have this pair, North Korea. Okay. So again, it will be 1 for the bigram also. Okay. So both of them are 1. So you'll get 1.
So 1 into 1 to the power 1 by 2.
Yeah, for 1 power anything, just 1.
Okay.
Okay. So the n-gram precision value would be 1, but if you include brevity penalty, then it will be very good because it is going to then penalize this short sequence. Okay. So how this brevity penalty calculates? It's the exponential of min of 0, 1 minus this. So length of the label, length of the predicted. Okay. So in my target, there are 1, 2, 3, 4, 5, 6, 7 words are there. Okay. So length of label is 7. Now tell me in the similar way, what would be the length of the predicted? 5. Right? So what will be the output of this first?
2 by 5.
2 by 5.
So minimum of 0 and 2 by 5, it will be 0.
0.
No, negative 2 by 5, right?
Yeah, negative 2 by 5. 1.
So there should be an exponential term coming.
Sir, how do we get 7? How do we get 7? Length of label 7.
1, 2, 3, 4, 5, 6, 7.
Okay, entire sequence of.
Yeah. Okay, 1 net was min there in the formula.
It's correct only. Then only you will penalize, right?
Yeah, but if min is there, then it's just going to
Then it
plan.
is minus, right? E power minus 2 by 5. Minimum of 0, comma minus 2 by 5 is minus 2 by 5. So exponential of minus 2 by 5, we are penalizing. Then only term will come. Otherwise, always min of 0, if this term is positive, 0 will be. So it will become 1.
Mhm. Is greater than half.
Is it pred by label or label by pred? Length.
It's labeled by pred only.
Oh, okay.
Yeah,
So,
if
sir,
we do that.
is the predicted sequence is shorter by any chance?
Mm-hmm. If predicted one is shorter in the label one, then we use. So
No, that's why we want to, that's what we are trying to avoid, right? If it is North Korea, then it will become 1. This term will become 1, the second term. So,
yeah, because in the slides, I think there was some problem here in the slides. Yeah. Enough fun is still the answer would be the same, that you are going to get exponential of 0. Okay. So that is not that whether you take min here. I mean, yeah, you will get exponential of 1. Mm, 1. That
Yeah, the formula seems to be correct with the lecture.
mm. Because even in the example that Faris took, he did not take the 0 here. Let's see. So I think something needs to be corrected here, but one formula that was there on the internet was that if the predicted sequence is greater than the true one, then you use the 1. Yeah, the formula is different. Yeah, in the example part, it is different. Yeah, that's what I was looking at. Because in that, sir directly took this value without minimum. Okay, I will check that, but something that I found on the internet, it's matches with that thing. So that if the predicted sequence is greater than the true sequence, then you go with the 1. Okay. Else you will go with this exponential of 1 minus length of true by length of pred. Okay, if predicted is less than equal to the true, the length of the sequence. Okay. So in our case, the second case becomes true. So we go with this part, exponential of 1 minus 7 by 5, so e power minus 2 by 5. And that's the same thing that sir also has done in the example.
So
Yeah,
what do we do now
okay.
for such kind of questions?
For now, go with this part. Okay. And I will just confirm this with the instructor once. Okay. And I will post it maybe in the discourse, or I will tell Puneet she is going to convey this in the next session. Okay. Which part we have to go with. Okay. But for now, as the example that Cyrus did, okay, that he used this thing, that if the predicted sequence is greater than the true sequence, then just take it as 1. Else, if the predicted sequence is less than the true one, less than equal to, then go with exponential of 1 minus 2 by predicted. Okay. So in that, you are going to get this part, e power negative 2 by 5, and you are just going to multiply it with this. So you're going to get final place.
So as of now, there is nothing to do with what is given in the actual formula.
Yeah, for now, like instead of this, condition, you can take this condition. That if the length of the predicted is greater than the length of the true, then the brevity penalty value would be 1. Else, the brevity penalty value would be e power 1 minus length of true by length of pred. Okay.
So does overall formula remain same? Brevity penalty into n-gram precision?
Yeah, overall formula, there's no problem in that. Okay. Why are we giving equal importance to unigram bigram? Ideally, shouldn't be more important to the actual accuracy than the other. See, what we are initially doing is we are taking the unigram precision, bigram precision and all. We are giving multiplying their precision part, and then till whatever the precision you are taking, okay, you are doing the square root reversion of that, or not just the square root, or 1 by that gram precision root you are taking. Okay, so it's not going to give the equal importance in some way, but whatever the highest precision you are taking, okay, that much power it scores. So it's kind of balance out. Okay, but in the multiplication, we keep it like the equal importance, because unigram is also important, like how much words you are able to correctly predict. Okay, then bigram, trigram is like in the sequence how many are correctly able to come. So they have equal importance there in that case. Or maybe there might be variants of Pleo in which you can do that, but for that I'm not sure of. Okay. Yeah. So shall we move ahead? This part I have to confirm. I was imagining that 1 by k to account for the fact that we are multiplying k terms. I have to read more about the, okay, and comment more on that. Okay. So now remaining from week 8 is the following formula: e power 1 by without the min 1. But GPT information we cannot directly take. I have to verify it with the instructor once. Okay. Because even if, like, for any question, if it comes in the quiz, then what the final thing you guys should use. So okay. So I will either post it on the discourse once I find it out, okay, or else I will convey it to the Puneet and he will convey it in the next session. Okay. Accept the blue. What formula do the degree level? Degree level DL does not have the blue penalty or blue score. Okay. It might be there in the LLM that I have to search for what formula they used, but in the degree level DL we do not have the blue as a concept there. Okay. The blue brevity penalty was not there. If it is there in the LLM, that I have to search for what they used. Now, one more topic is remaining, that is the beam search. Now, sir has not covered it fully. So I just covered the intuition that was there regarding the beam search. Okay. So what currently our prediction strategy is that for the words that we are feeding, okay, we are going to get the output. And how we are deciding our output? It's the most probable words based on the softmax normalization that we are doing. Okay, so based on after applying the softmax, whichever word has the most probability, that word we are going as a prediction. Okay, but as here we are doing with the greedy strategy. Okay, as we are greedy for the probability prediction here. Okay, but it's not always the case that the most probable word is our correct sequence word. Okay. So what beam search do is, instead of just taking one highest probable words, it's going to make use of some k highest probable words. Again, k is a hyperparameter here. Okay, that is up to you to decide. So it's going to take these k highest words probability, not the probability, those k highest words, and it's going to search for that using these k different highest probable words, how the sequence will be generated. Okay, and then in the end, using the joint probability of these sequence, whichever is giving me the highest joint probability, we are going to take that sequence as an output. So this is the beam search. Okay, and beam search is technically becomes your greedy approach when you set this value of k to be 1, because in that case it's just going to take the highest probable word. So that's all for beam search. Is it clear?
Sir, can you repeat the last part, please?
Yeah. So is the idea for beam search clear? What it does?
No, sir, no.
Okay. Let me repeat. So currently what we are doing is, for one word that we are feeding as input, we are passing it through the layers of hidden state, then output layer we will be having. And in the output layer, we will apply the softmax, right? And then in that, what we do, whichever word has the highest probability. So let's suppose the output of softmax, we have only three words in our vocabulary. I love DL. Okay, so we are going to get some probability, let's say 0.5, 0.3, 0.2 after applying softmax. So what you are going to do, because I has the highest probability, you are just going to predict the word as a I. Okay, that was our greedy approach. This is called greedy because we are greedy for our highest probability. Okay. Now, in this, what the one problem is that it is not necessary that the sequence that you are going to get after using this greedy approach, that every time you are just using the one word, and that is just the word that is getting the highest probability to generate the sequence. Okay, but this necessary need not to be the true sequence or good sequence. Okay, and the another way for doing that is by doing with the beam search. What it does, instead of just using one word with the highest probability, we are going to use k words with the highest probability. So let's suppose we use two words with the highest probability. Then using the I and love, we are going to generate the later sequence, the remaining sequence. Okay, and we will see the sequence generated by both of them. Okay, find the joint probability for both of these sequence, whichever is giving the maximum joint probability, we are going to take that as an output. Okay. So in simpler words, instead of just using one highest probability word, we are making use of multiple or k highest probable words and trying to generate sequence based on all of these k. So instead of just trying with one combination, we are trying k multiple combination and see how the things goes in the future. And whichever gives us the best result, we will just use that as our output. Okay. Now, the thing that I said in the end was that if you set the value of k to be 1, then it's similar to your grid search. That is, if you set the value of k to be 1, then it's just going to take the highest predicted word. Okay, and that was our greedy approach that we were doing it till now. Okay, is it clear now?
This is going to take more
yes.
right?
Yeah, this is going to take more time now. Okay. Because of course it's going to try out this different combination every time. So of course it will be a little computationally expensive.
And whatever these week 8, what we discussed is all variants of RNN.
RNN. Yeah. Encoder decoder, you cannot say technically a variant of RNN. LSTM and GRU are the variant of RNN. Okay. Encoder decoder is the architecture. Different architecture
It's
that
a
we use.
different architecture, yes.
Okay. Now, Any doubt in whatever we discussed for week 8? Because
Sir,
still,
after generating the sequence of bit with the most probable word, we will find the blue score.
yeah, you can find the blue score to see. See, generally, like there are different metrics, which metrics you want to use. So blue score is one of the metrics to see how good you are performing. There's something called as word error rate. Okay. So it's like the number of words that were not there, the number of new words that come up or something like that. Okay. So there are different metrics. Blue score is one of the metrics to evaluate how good your sequence is. Okay. So it's similar to like for your general classification case, you have the accuracy, F1 score, precision, recall. Okay. For your regression, you have root mean square, R2 score, mean absolute error, something like that. Okay. Give me 1 minute. I am having one call. Sorry for that. Yeah, so what I was saying that blue score is just a matrix for you to use. Yes, Shubhra.
Sir, this is not related to week 8. This is more of a uh, technical issue regarding the dashboard, the course dashboard. Can I ask right now?
Just wait a minute.
Okay.
So anyone has any doubt in the discussion for week 8, whatever we discussed? Any more doubts regarding beam search, Blaze score, encoder decoder architecture, bidirectional RNN, LSTM GRU? Okay, good. Yes, now you can ask.
Are we doing a revision session also today, sir?
No, no, not today. It's already the time is up. The revision session we cannot do. Maybe I will share some question on the discourse. Okay, I have some extra questions from week 5 to 8. We are not going to share any more question from week 1 to 4. I will be just sharing some of the question from week 5 to 8. If I am not able to take any revision session, okay, that I will be sharing on the discourse. So I will recommend you guys to active on the discourse. So maybe by Wednesday or Thursday, I will be sharing some extra questions, okay, that you can look at. Or else the
Okay,
mock
sir.
will be released. In the mock, we will add that, if not on the discourse, okay.
Sir, when will the mock be released?
For now, I'm not even sure whether we are going to release the mock or not. Okay, so
Okay,
we
sir.
have to check. If mock is released, then the question will be there in the mock. Link the WeChat GPT. That is something that we use for. Okay. It's actually confidential notebook for the question. Okay, so that just an image that you can find on the disk online. Okay, if you want that image, or else I can just share that image. Okay, otherwise, other than that, there are just question in that notebook. Okay, nothing else was there. Yes, Shubhrat, you had any doubt, right, regarding the discourse or dashboard?
Yes, sir. Just a second.
Do you want to share your screen?
No, sir. Actually, I was just checking this thing. Actually, after quiz one, in my dashboard, the result for that was not updated. And initially, I did not feel any discrepancy for my because in the live sessions also, Levin sir was saying that the dashboard score update might take some time and also I did not do it that. But after that, found that in quiz one, I was mentioned as absent, and in the Looker Studio also for my deep learning exam was not mentioned. So I mailed the technical team, like I sent them screenshots of the Looker Studio and the dashboard and they sent that your attendance is recorded and everything, so you should not worry. But now I'm seeing in the dashboard, in the allowed to take end-term exam, it is mentioned to be decided for me. And in all other subjects where the where my attendance was registered, I am allowed to take the end-term exam.
It's
So I'm
for
really not sure.
everyone. It's for
Uh,
everyone to be decided.
Okay, okay. Then thank you. I thought it's only for me, so I was worried that probably because of my absence in quiz one, they have made that.
Same for me.
Okay, thank you,
it
sir. Thank you.
might be because it's the new course, so things sometimes take some time for us to process. Okay, for this part. When the result of NPP will be announced. Okay. The score that you can already see on the Kaggle platform. Okay. And if you have done the required part that was there in the evaluation, okay, then the remaining score will be there. So only the 20% weightage that was there for us to evaluate, okay. Only that part is remaining. So till now we have not got the responses yet from team. So I don't think so in this week. Then next, maybe by next to next week, you can get. That's my estimate. Okay. So,
And sir,
any-
I just also wanted to ask because I've not seen the week 8 lectures so far. Like, should I watch those lectures also in this TA session also, or like this TA session is enough because like other projects and the exam is also near. So
uh,
like, for the
see,
exam perspective, like.
uh, for the exam, yeah, you can watch the TA session only. Welcome, Karthika. Uh, okay. But if you want a good understanding, then I will recommend the lectures. Okay. As I have not covered everything in full deep. Okay.
Okay, sir. Okay. If I get time, I will try it. Thank you.
If you just want an overview, then you can just watch the TA session.
Okay,
Yeah,
sir.
please fill the feedback form. And any more doubts? Anyone? Okay. Thank you. Thank you all for joining. And thank you for filling the form.
Thank you, sir. Good night. Bye.
Good night,
Thank you,
everyone.
sir.
And yeah, for the NPP, see, as I told, like we have not yet got the notebooks from the